6-2, confidence intervals for the mean if you have a smaller sample. In 6.1 we said, well, if we have a big one, and sometimes we knew the standard deviation, sometimes we didn't, and if the sample was large enough, which was 30 or more, we could just use the sample standard deviation. We didn't have to find the actual one. Well, now we're going to talk, what if we have smaller samples, and what if we don't know the actual standard deviation? Because if you ever know the actual standard deviation, you can just go ahead and use the z-scores that we were using before from the standard distribution. Here we're going to learn a little bit different distribution today, but we do have to talk about degrees of freedom first. It's an interesting idea, and it's a very difficult concept for some to understand, and so I tried to come up with a few other examples that were not statistics-based to help you out. But first, let's just kind of look at the definition here. Basically, they say degrees of freedom are the number of values in the final calculation of some number, or some statistic as it is in this class, that are free to vary. So some of them can be whatever they want, okay, and some of them cannot, is basically what we're saying. But what we want to find out is which ones can actually just kind of be whatever they want, which ones can vary. And then, like I said, next we're going to take a look at a couple of examples that maybe are more familiar to you or would make more sense to you, and then we'll talk about how many things can actually vary in that problem. Okay. Give you a second to write that down, and I'll go on. All right. So here I've given you two, again, more general examples. So the first one says, given the equation x plus y plus z equals 100, how many variables are allowed to roam? Or basically I'm asking you, how many are allowed to vary? How many degrees of freedom do we have? And basically you can just pick one of the variables and say pretty much, can x be whatever it wants to be? Well, if I only have one equation, yeah, x can kind of be whatever it wants to be. Maybe x could be 5, maybe it's 20, maybe it's 200, who knows? All right, it could be anything. And for that matter, if I just choose another variable, maybe the y could also be whatever it wants. So maybe x is 20, y is 50. At that point, to make this equation true, can z be whatever it wants to be? And unfortunately not. Again, if this chooses to be 20, that chooses to be 50, well, that's 70. Z has to be 30. So basically, any two variables up there I choose, I can make them whatever I want, but the last variable up there has to basically make all the variables add up to 100. And I could even make x, negative 20 and y negative 50, and then z would just have to, be what, 170. But or z would be, excuse me, that last one kind of tells you what it has to be. So how many are allowed to roam? Well, if you want to look at it one way, x and y are allowed to roam, and z has to kind of make it happen, or you could say y and z can roam, and x has to make it happen. But basically, two of the variables are allowed to be whatever. And so for this one, the degrees of freedom, which is abbreviated df a lot of times, as you saw in the definition, degrees of freedom for that particular problem is 2. 2 of the values can be whatever they want. For example 2, I'll have to add a little bit there. I'm going to let you think about that one now that you've kind of seen one. So it says, I need to take 10 classes to get my master's, and only 10 classes are offered. Then how many degrees of freedom exist? And let's kind of say that those 10 classes are offered every semester. I actually don't even have to put that, but basically there's only 10 possibilities, and I need to take all 10. So how many degrees of freedom do I have? That's kind of a more difficult one, but I look at it this way: that first semester, I could take a first class, and then the second semester I could take a second class. I don't have to take them in any particular order, but as I get down to the end, I have fewer to choose from. So at the end, after 9, if I only take one a semester, after the 9th semester, I have to take that last class. That 10th class, I have to take it. I don't have a choice anymore, all right? It has to be that class. Up until then, I had other classes I could choose from, okay? But at the end, that last semester, I only have the one class to choose from. So in the first semester, yeah, I can roam. That can be whatever. The second semester can be whatever. All the way to the 9th semester can be whatever. But in the last semester, it has to be that particular class. So the degrees of freedom here, the things that are allowed to roam, the degrees of freedom here would be 9, okay? Because that last semester, I don't have a choice. Okay. And that's kind of how some people look at it. Is there a choice when talking about degrees of freedom? It's one way to look at that definition. All right, so now that we've talked about degrees of freedom, let's kind of move on. If sigma is unknown and n is less than 30, so this is what they're talking about by a small sample, then the sampling distribution for x bar is a t distribution now. It's not a z distribution anymore. Okay? Remember, if you know sigma, and if you're greater than 30 or equal to 30, you're good. But you can just use, it's a standard distribution, you can just go with it and use your z-score. But here we're actually going to use like a t-score, basically. As long as the random variable is normally distributed or approximately normal, okay, then you can actually use the t-distribution. I've tried to give you some pictures here. In the picture at the left, you see that degrees of freedom goes to infinity for the black graph. That's pretty much verging to your z-score. That's your standard distribution right there. And you see for the blue, for example, degrees of freedom 5, you see that it's close, it's getting closer, but you can see that the tails are thicker on the left and right. And if you go degrees of freedom only 1, I don't know, what is that, orangish, I guess? The tails are even thicker. That's because there's so many things, you know, there's things that are allowed to roam, and so they have to take that into consideration. I also like the picture on the right that shows you the standard normal distribution in the blue there, and it shows you even about where 95% is underneath, which is nice. And they show you to get 95% in the t-distribution, you have to go much wider, because you can see definitely, and you know, please notice that they zoomed in a little bit on the one on the right. On the one on the left, they go out to about -5 and +5 for z-scores, or t-scores, and here they're only going to -2 or about 3-ish. So that's why it looks a little bit different. But here they're saying for n equaling 12, which would be, you're going to learn n equaling 12 means there's 11 degrees of freedom, because one of the values has to kind of make things happen. The other 11 can be whatever, but that last one has to make things work out. And you notice, yeah, the tail's much thicker here. But it is still bell-shaped. It's still centered around the mean. Okay? It's still symmetric. Okay? So it has all the properties of z, it's just not the same shape. But as you notice on the one on the left, as degrees of freedom gets larger, or the bigger the sample basically, the more it goes towards the standard distribution anyways. Which is why we get to use that. Once we get past 30, it's so close that we don't even bother anymore. So as it says down here in the green, the degrees of freedom for a t-distribution is basically n-1, because we're basically using a sample standard deviation because we don't know sigma. So we're using a sample, and so the degrees of is 1 less because we are using that estimate. It's another way of looking at degrees of freedom. I'm using an estimate in there. And we'll also talk about n-1 because you've seen that before. When we found the sample mean, or the sample standard deviation, we would divide by n-1 instead of just n. And that's, again, because we were taking estimates. Okay, and so that made it more accurate. So as the degrees of freedom increase towards 30, the distribution very closely aligns with the standard normal distribution, as I said already. Okay, so it's used the same, but it's used at a different time. This is the t-distribution is used when n is less than 30 and you don't know sigma. And that's when you're going to use this. Okay. After that, it's very similar to what we did with the z-scores for confidence intervals and all of that. So right here, determine the critical t-score, so it's TC is what they call that, for 95% confidence interval with a sample size of 15. So the first thing, whenever you're doing this, is first decide, can I use a z-score or not, or do I have to go with a t-score? And obviously this one tells you t-score, but why is really the question. Well, here I don't know sigma. That's a good tip-off. And on top of that, n is less than 30, and because we only have 15. So we have a sample of 15, which really isn't very big. And so n is 15, which means degrees of freedom here is 14, because it's always n-1. And we know that our confidence interval that we're talking about is 0.95. And at this point, what we have to do, and what we're going to look at is, seeing we want confidence intervals, we're going to do two tables, is you look at your table. Okay? And so I believe I have mine right down here. I believe this is similar to the one that you got handed out to you. And notice on the top it says cumulative probability. That kind of goes back to almost what we were talking about when we were kind of doing the correction for continuity. And then you have a one-tail, two-tail on top here. We're going to be concerned with the two-tail. But a lot of times you don't even have to necessarily look at that, because you just find your degrees of freedom, which for us is 14. And then you find the confidence interval you want, which is 95. And where do they hit? Well, they connect at 2.145. So that's your t-score, which is very, very similar to a z-score, if you would want to look at it that way. Okay. And that's all they wanted to find, the critical t-value, 2.145. Again, that's kind of how many standard deviations out it is on the t-distribution, which is slightly different from the z-distribution. Not by much, but it's, as you saw in those pictures, but it is just enough. Okay. Any questions on that? Good. Well, now we're going to go for, and so you basically just use the table the same way. Now we are going to go for margin of error, and you're going to, this formula is going to look very, very familiar. Okay. Your error is it's just like before, it was your z-score, or your critical z-score. And then on top you see s instead of sigma, because remember, we don't know sigma for this one. So we're going to use the sample standard deviation, which is what that s is, divided by the square root of n. Now right there, we're not dividing by the square root of n, because basically we've already divided by n minus 1 along the way when we found standard deviation, if we actually had to go find that. Okay, so that's your error. Remember, that's plus minus always. It could go either way. So here you randomly select 16 restaurants and measure the temperature of the coffee. The sample mean, or the sample is 162 degrees with a standard deviation of 10 degrees. That's quite a bit. Determine the 95% confidence interval for the mean temperature. Assume the temperatures are approximately normally distributed. So once again, the first thing you should always find out is, are we going to do a z-score here, or are we going to do t-score? And the one thing is, do you know sigma? And no, because it says sample standard deviation. So sample standard deviation is the s. Right? And then, well, even if I just know the sample, if n's bigger than 30, we're still good. 30 or bigger, but it's not. N is 16. So we're going to have to go t on this one. So we know n is 16, which means degrees of freedom, because it is approximately normally distributed, so we can do that. Degrees of freedom then is 15, and confidence interval is 0.95. Now that's what we need to know to go into that table, basically. Right? And so to go into the table, we have to find, basically what we're going to find is the t-score, which it kind of goes right in the middle up there. We're going to find that, right? Because we already know the other two numbers. Okay? So E is going to equal, well, let's find out. So we know degrees of freedom, we know is 15 that we need, so that's down here. And we know that we got 95%, so right there. So it's 2.131. So 2.131 times our sample standard deviation is 10 over the square root of, rather nice number, of course, 16. It's a nice number because I'm doing it. And so you find out your error. That's how far you can go either way. And you notice this is 2.131 for 95%, which is a little bigger than 1.96 that we had before. But that kind of goes back to that picture we had. And I got 5.3275. All right, 5.3275 is what I got. Now, unfortunately, that doesn't really answer the question. The question wanted a confidence interval. Okay? But remember, that's how far I should be able to move. So we're saying the mean, the actual mean, not the sample mean, the actual mean is basically the 162 that we have plus and minus the 5.3275. And so on the low end, 156.6725, and that's degrees. And then the high end, that's relatively easy math on that one, right? Just add 5 to that. Now remember, that means that if I did this, say, 100 times, 95 of the intervals that we came up with would actually have the true mean in it. We don't know the true mean, but we know from all our experience that 95% of the time, the actual mean would be in that interval somewhere. It could only be 157. It could be 160. Who knows? It could actually be 162, which is the sample mean. But we really don't know. But we're trying to get an interval that we know we're 95% sure what's going to happen. Why don't you take a second here to try example 5 on your own. All right. Of course, that wasn't a lot of time, so you should probably pause it if you're actually working on it. So if you're at your computer at home, just pause the recording. Or if you're sitting right here, you can always just tap the screen, whatever it is you got to do. So first thing I always like to do is kind of figure out, well, am I talking T or Z? And so you randomly select 20 mortgages. Okay, so that's below 30, but I still don't know that I'm necessarily going to go T. Are determined for the current mortgage interest rate at each. The sample mean is, there's a sample mean, that still doesn't help me either, 6.93 with a sample standard deviation. See, now I know. I don't have actual sigma, and so we know we're going T. And so we know the means right there. Our C is 0.99, so pretty wide interval probably on this one. N is 20, which means degrees of freedom. With the number of those 20, 19 of them can kind of be whatever they want. That last one kind of has to make things work out. And so we also have S. So of our formula, we know that E equals something. That's what we're going to go find in the table. And 0.42 over b square root of 20. But we have to go find what is that particular t-score. And so it's in blue. So we find degrees of freedom of 19, which is the second from the bottom here. And then we kind of go over until we get to 0.99, which I came up with that number right there. Okay, so that's going to go right up here for us, 2.861. So go ahead and calculate that quick if you haven't done so already. Hopefully you actually paused it and actually tried that. It should be no surprise that because of this problem, this is a much smaller answer than in example 4. But once again, keep in mind that is talking about the error. You can go plus minus that from the mean. So we know the actual mean, we're saying, at 99% confident that if we take 6.93 and add and subtract that number, which isn't very big, so this is good, that we're going to get the actual mean in there 99% of the time. And I got 6.661 and 7.199 is what I got for my interval. And based on our information, the mean should actually be in those intervals I come up with 99% of the time. And the last one. Randomly select 25 newly constructed houses. The sample mean construction cost is 181,000. Population standard deviation is 28,000. Assuming construction costs are normally distributed, construct a 95% confidence interval for the mean construction cost. I hope in reading that, you realize what we're going to have to do. This isn't going to be T. I know it's only 25, but if you know the population standard deviation, you can just go ahead and use a normal distribution. So that's what we're going to do. So we don't have to worry about degrees of freedom. We know N is 25. We know our confidence that we're looking at is 0.95. And so what we're going to do is go back to our old formula, which is Z critical score times sigma. See, that's the key. And again, if you're above 30 in this formula, you can just use S for sigma up there. But if you're below 30, you have to actually know sigma. But if you know it, you can use it. And so if you remember from the notes the other day, our 95% Z-score is the one I told you to kind of remember. It's the most commonly used. It's just 1.96. You could look it up if you wanted to. We know we've got sigma is 28,000, I believe, right? So 28,000 and square root of 25. Again, the key is you got the population here. And you do that calculation over here, and you get 10,976, or approximately. But again, that's your error. What that means is I've got to go from the mean both directions. And our mean is 181,000, so I got to go 181,000 plus minus that, right? And so I got 170,024 and 191,976. Again, basically if you picked some you know the mean, if you picked some sample of your own that was about the same size, about 25, you would believe that the mean of those 25 that you picked up would be in between these two numbers 95% of the time. Now you're wondering, some of you probably, what if I would have done the t? How would it have changed? In all honesty, not a whole lot. I actually did that calculation, and this is from z. So this one down here, I did the t, and it came out to be very close, but there's kind of rules you got to follow as to when you use what. The reason that we want to start using degrees of freedom in the other one is because we're using this sample standard deviation. And so that means we kind of we need one of our values to be exact. Well, here I don't necessarily need any, because I know if I have the population standard deviation, that is exact. I didn't use anything to estimate. Nothing has to vary. Or basically you could say it can all vary if you want to look at it that way. Okay, either way it could be looked at. And so that's why this gap down here, if you use the t, is a little bit wider, but that makes sense because the tails are wider. Okay, so it makes sense that that gap gets a little bit wider. Any questions? Just watch out for t versus z. If you got the population standard deviation, please use it. If n is greater than or equal to 30, it doesn't matter either way, really. But it's normally said to just use the z at that point. If you're less than 30 and you don't know the population standard deviation, and it's normally distributed or about normally distributed, use t. And really the only difference comes into the formula. This is a t, and if you're using t, you obviously don't know that, so you're going to put an s there. And then really it's the only difference. It's a slightly different distribution for you.